Oh yeah, sound waves, here we go. Hopefully this is my last video of the day. Did I turn the sound off? Oh, I forgot. Let's do that real quick. All right. So page 45, volume 3 of the workbook has some figures that will probably help. A lot of this is taken from there, but let's just try to dig into it and then let's see what happens. So sound waves are longitudinal waves. They're like waves on a spring, not like string waves. And so actually, let's get to a quick visualization of this. And then I can zoom out a little bit, scroll up. So if you recall a longitudinal wave, this is kind of a cool apparatus. I'm coming around to the front. So you could imagine if I pull this spring down and let go of it, you could see some wiggling on there, but it's happening so fast, it helps to have something to slow this down. You can't really see the wave pulse on the spring that well. So let's actually imagine this situation. As I turn this crank, I want you to watch this area. Notice that at some point, these rods get bunched up and these ones get spread apart. And notice that bunching effect, that compression, propagates. And now at the next revolution, it's down here, we see a compression. And if I just start turning this part of it, of the system, looks like a longitudinal wave, whereas this one over here is a visualization of the transverse wave, so like a wave on a string. This looks like the normal sine wave you'd see on a string, whereas right here we do see this interesting set of compressions. We see this compression blast through there. Boom. Boom. All right. And then one more. Oops. Just getting this set up. I got my backdrop fell down. Just a second. This was the other example we showed, I think, in a previous video of a longitudinal wave. Hopefully that shows up a little better. And so, again, notice the medium, in this case, are these vertical rods. The disturbance is when I wiggle it. Notice that elements of the medium, the rods, on average stay in place. They might have a small displacement from equilibrium, forwards or backwards. Right? Sometimes they wiggle away this way, sometimes they wiggle this way. So they're displaced forwards and backwards, and you'll see a bunching or a compression kind of propagate down the line there, right? So you can see there's a compression, and then notice there's also regions where the rods are spaced far apart. The term for that is rarefactions. Let's go to the board and get this stuff written up. Come on. Get this out of here. Get this out of here. Put this down like that, just so I can work. All right. So now, look, we all know sound waves go all over the place. They spread out. Let's start simple. Okay, let's keep our analysis right now to a sound wave in a pipe. Okay, and then we'll talk about sound waves emanating spherically later. So here, I want you to imagine, basically, this is what a speaker is. It's a piece of paper that's wiggling back and forth, or some polyurethane, or some kind of membrane that's wiggling back and forth. That's what a drum is. You hit a drum, the membrane wiggles back and forth and emits sound waves. So right now, let's say this membrane or whatever is trapped inside a pipe. So what's going to happen is the air molecules are going to get bunched up at various, so this is a snapshot in time. This is really wiggling back and forth all the time. And then the waves are just going to keep traveling down this way. And so we see right here, this area is a compression. And it's just hard to label it. Let's just get this back in here. So there's a lot of molecules in some places and not much. So this is a compression. Let me label it here. There's a lot of stuff I want to label in here, so sorry I'm taking too long. And then these areas right here are called rarefactions. Rarefied air. There's less air there than usual. And so immediately this kind of brings up, we usually talk about air pressure. Now, when you are breathing air in the atmosphere, we assume that atmospheric pressure is, generally speaking, close to 1 atm, but we don't use those units in physics. We use 1.013 times 10 to the 5th pascals, where a pascal is a Newton per meter squared. Force per unit area, pressure is force per unit area, force is a Newton, area is meter squared. All right, so what's really happening here is I obviously didn't draw every single air molecule in this pipe. There's moles and moles of them, 10 to the 23 molecules in here or more. So what I'm really trying to emphasize here, it's not that there's no air molecules here, it's that there's less compared to normal. So this is the concept of overpressure. And to be clear, overpressure could be a positive or a negative number. You could have a positive overpressure, having a small pressure above atmospheric, or you could have a negative overpressure, a small pressure below atmospheric pressure. All right? S is going to be the variable we use for displacement of molecules from their average position. Remember, the molecules aren't going anywhere. Energy is traveling down the wave. But on average, the molecules are wiggling back and forth, just like this oscillator's wiggling back and forth. But as the molecules all collide together and send this energy down the tube, the energy is traveling, the wave is traveling, but the molecules on average stay in place. All right? What else did I want to say about that? Let's call that good. Now, I will make, I'm going to go into these equations in just a second on the next board, but before I do that, I do want to briefly talk about this sound wave emitted spherically. So you can imagine, sometimes what we'll do is rather than drawing these dots all the time, what we'll do is we'll say, you know what, let's make this simple. I'm just going to draw a line everywhere I had a compression. And then I'll erase everything else. And this is all in your notes. All right, sorry I'm taking a while here. But this is a little bit easier to see. And right, imagine trying to draw, so these are the wave fronts. You could think of them kind of like the crest of a string wave, even though they're not string waves because they're not transverse. So a lot of people think of this like a wave crest, trough, crest, but these are, you could also call these wave fronts. So a lot of times you'll see in books, instead of drawing all the dots, you'll just see lines like this. That's particularly useful for sound waves emanated spherically. So we have spherical wave fronts. Now to be clear, they're not circular here, they're spherical. So just to give you a visualization. Oops. I'm coming back, don't worry. You could imagine the source might be a speaker about this size. And maybe the sound is spreading out, maybe not perfectly spherically from a speaker, but approximately spherically going out in every direction. So people all around the speaker can hear it. You could argue, could it be hemispherical or this and that? Let's start with simple. Let's just say it's going spherically. First, the sound wave energy is on the surface of this ball. Then it's on the surface of this ball. And as the sound wave propagates out, eventually you've got this huge area and all that energy is spread out over a huge area. All right, so that's what's happening when you have these sound waves spreading out spherically. The energy is being emitted and it's being the intensity of the wave. We'll do another video on that in a minute. Let's just get through this. So now we've talked about the longitudinal versus transverse. We've talked about overpressure and displacement. Let's dig into these two a little bit on the other board. Okay. All right. Let's get this demo out of here so I'm not looking at it on the monitor. Where'd I put my markers? There they are. All right. So the equations that we're going to use in this book are going to be, this is the displacement as a function of position and time. And to be clear, we're kind of thinking about sound wave in a pipe here. So this is that sound wave traveling down the pipe. You could think about the displacement of one of the air molecules that's at this position and at this time is given by some amplitude, and there's a cosine. You might be saying, hey dude, what about the phase angle? You're right, good for thinking about that. Let's just assume the phase is there for this chapter and keep it simple. We could discuss phase angles in a later problem, but well, you'll see what we do later. So for now, let's just assume we start the clock such that cosine doesn't need a phase angle. All right, so to be clear, the maximum displacement, positive or negative, does not happen at the rarefactions and compressions. That's kind of interesting. It happens halfway between. The rarefaction, I want you to think of as a pressure minimum, or I should be careful, an overpressure minimum, which is also a local pressure minimum. And then compressions, I want you to think of as an overpressure maximum. So I think it's probably easier to start with the overpressure and be like, look, when the molecules are bunched together, it makes sense that there's a lot of pressure. So it seems reasonable that a compression where all the molecules are stacked together should be an overpressure maximum. And then it turns out the displacement is exactly the opposite. So why do you get an overpressure maximum? What will happen is, when we have this thing going, let's find a nice one right in the middle. Let's say right about there. So what's happening is, at this point in time, which rod is that? It's hard for me to see. This rod right here is near the top of the circle, which means as I turn it, this rod is barely moving at all. And notice, at that point, that's where we kind of get the bunching. So you're getting the overpressure maximum wherever the rod is not moving, because all the other molecules are being moved towards it, and you get this overpressure maximum. That's a subtle point. Hey, if you don't like learning that, that's okay. Let's just get through this. Let's move that out of the way. All right, close enough. So what you need to know is this. Overpressure max occurs at a compression, overpressure min occurs at a rarefaction. And then halfway between those, you'll get the displacement maximum, right? The molecules have moved away from those spots towards these. All right, interesting side notes. The overpressure maximum relates to the displacement, as you could see by all these demos I'm trying to show, where in this case, this is the speed of sound. This is the density of the medium. And that could be air, it could be steel, it could be water. Sound waves can travel through fluids, they can travel through solids. All right, and then omega, that's frequency, angular. So we could see that the displacement, the displacement maximum, and thus the displacement in general, relates to the overpressure through these parameters. If you care, a little bit of bells and whistles before we leave this topic. This term right here is called the bulk modulus. If you recall from chapter 12 in Physics 161 or your intro physics class, the bulk modulus describes how compressible a material is. So if a material has a large bulk modulus, right, if it's hard to compress, like say steel, you might get a higher speed. However, this term on the bottom is density. So obviously air has a very low density, so that's going to help keep the speed of sound high. You could imagine if you replaced air with helium, the speed of sound might change, and that's the origin of the weird voice thing that you're not supposed to do because those balloons are coated with stuff now or whatever, right? Whatever. Speed of sound depends on temperature. This room happens to be cold a lot, so it ends up being a little bit lower than the usual, but typically we assume 343 meters per second is room temperature, and the density of air is about 1.2 kilograms per meter cubed. So a weird, I think it was Hewitt. I read this in Hewitt. A typical refrigerator is about a meter cubed of area, and then 1.2 kilograms is about the mass of a dozen eggs. So, which is kind of interesting to think about. That's a little bit more air than you think about, a little bit more mass in air than maybe you expected. So the mass of air in your refrigerator is approximately the same as the mass of a dozen eggs. That gives you an idea. It's light, but it's not zero. It's something. Let's go ahead and wrap this video up and stop the live stream.